All right, happy to be here. I'm going to tell you about constraint majorization and its applications in mechanism design. So a typical framework in mechanism design specifies an objective function and optimizes it subject to incentive constraints. For example, think about revenue maximizing auctions, right? Or even simpler examples like the monopoly pricing problem. So what we do is that we extend this framework. We extend this framework by incorporating additional side constraints, or if you may, feasibility constraints. Let me give you some examples. In monopoly pricing, the monopolist may want to maximize profit, but may be subject to a price cap constraint. In procurement auctions, there could be budget constraints that the auctioneer faces. In contract or auction design, the objective could be maximizing profit, subject to welfare guarantees or efficiency guarantees. Another area that has been recently also studied is redistribution in two-sided markets. So the idea is facilitating trade between buyers and sellers in the two sides of the market. And this has been studied with the objective of maximizing efficiency. However, the planner may want to add additional constraints, for example, on the welfare of each side or the induced inequality after redistribution. So what we do is setting up a general framework that captures these applications. And we also study how much each additional constraint can complicate the structure of optimal mechanisms. And the observation generally is that one additional constraint does not complicate the structure of optimal mechanisms much. And we also provide a regularity condition, which, if it holds, it guarantees that the general structure of optimal mechanisms will not change in the presence of one additional side constraint. OK, so let me be a bit more concrete. I will start with an application in monopoly pricing. Then I will tell you about the results that are behind analysis. And finally, an overview of other applications of the abstract results about extreme points of function spaces. So before diving into the model, let me give you from a high-level perspective what happens in the monopoly pricing application. So this is a classical framework. There is one monopolist and a continuum of agents, let's say buyers. From classic results, it implies that the optimal mechanism is a menu of at most two options. So there will be a higher quantity sold at a higher price, a lower quantity sold at a lower price, and every buyer is free to choose either option they want, or just stay away and don't buy anything. What we show is that in the presence of this additional feasibility constraint, the cost, basically, of this additional constraint is one additional menu, one additional option on the menu. So basically, the optimal mechanism would be a menu that has at most three prices. And then the regularity condition that I described earlier, if it is satisfied, it will guarantee that two options will remain sufficient for optimality. And this is a condition on the distribution of agents' valuations. OK, so let me be a bit more precise. Here is the model. There is a unit mass of agents. Agents are unit demand in the sense that they demand at most one unit of object, and objects are divisible. Each agent has a privately known valuation V. If she receives the object, a fraction x of the object, in exchange for a payment P, her payoff equals Vx minus P. OK, so the standard quasi-linear form. The monopolist owns a mass n of objects. This mass is supposed to be less than 1 without loss of generality because the mass of agents is 1. And the monopolist values each unit of this mass V0. So the monopolist knows the distribution of agents' valuations. His objective is maximizing profit. subject to a feasibility constraint. So let me give you some examples of what type of feasibility constraints we allow, and you can pick your favorite. The rest of the results will go through. The first one is a price gap, as we discussed earlier. So more precisely, the price charged to any agent per share of the good should be below a cap. Okay? Another type of feasibility constraint is that welfare should be a lower bound guarantee on welfare. So welfare should be above a threshold where we define welfare as the agent's average payoff. Another one is a similar guarantee, but for efficiency, where we define efficiency as the sum of the agents and the monopolist valuations for owned goods. Okay, so you can pick any of these three. The rest of the results that I say we'll go through. There is another type of constraint that our framework allows, but I wouldn't cover in this talk. You can see the paper for that. And these are inequalities. These are basically upper bound guarantees on the amount of inequality induced after distribution of the good. And we measure inequality in the sense of Lorentz order. But again, this is outside of the scope of the talk. OK, so some standard definitions. A contract is a tuple xt. Allocation rule is x. It is defined from the space of valuations to the unit interval. The payment rule is t. It's defined from the space of valuations to non-negative reals. A contract is incentive compatible if, in the usual sense, if no agent has incentive to misreport our valuation, v to some other valuation, v prime. A contract is individually rational if no agent gets a negative payoff from participation. So this is the second constraint. And a contract is feasible if it satisfies the feasibility condition that we specified earlier in the previous slide. Okay, and here is the key definition on the slide. We are looking for the optimal contract. What is the optimal contract? That's among the space of all feasible, incentive compatible, and individually rational contracts. We are looking for the one that attains the highest profit. Okay? So basically, you want to see how does the optimal contract look like. And first, I will define a class of contracts that contains the optimal contract. These are the class of menu-based contracts, I call them. So a list of, these are basically a list of options, price, quantity, pairs. And if an agent picks a pair, she will receive quantity QI for a price PI. And people can look at these options and pick one of them if they like, or just don't pick anything. So like I said earlier, from classic results, it follows that without a feasibility constraint, optimal contract is a menu-based contract with at most two options. Okay, so two options are sufficient for optimality. However, when we have a feasibility constraint, like the welfare guarantee that we discussed earlier, or the price gap, we show that menu-based contracts may need to use three options, and three options are also sufficient for optimality. So the cost of one additional constraint is one additional option on the menu. I also told you about this regularity condition, right? If it's satisfied, basically means that the general structure of optimal mechanisms will not change. In this case, we will see that two options will remain optimal. So what is the regularity condition? Define the virtual value function in the usual sense. So that's v minus 1 minus CDF of v divided by its PDF. We say f is regular, the distribution is regular, if the derivative of the virtual value function is quasi-concave or quasi-convex. So this may look like a complicated condition, but it turns out that it's actually satisfied for many common distributions. So that I've listed here, we prove that it is satisfied for beta, Pareto, Rayleigh, uniform, and Weibull. For the rest of the distributions on the list, we do random sampling or grid search, and we haven't found a counterexample. And maybe also it's worth mentioning that neither this regularity nor Meyerson's regularity imply each other. However, some of these distributions that I list here fail to satisfy Meyerson's regularity. And if the condition holds, then Like I said earlier, 2 options will remain optimal, so there is no cost from imposing an additional constraint in terms of complexity of the structure. Okay, so next I want to tell you about the abstract results that derive the analysis in monopoly pricing. And these are results about extreme points of function spaces. And finally, I'll tell you about applications of these results to other economic problems. So the objective in this slide is some preliminaries. And the objective here is defining these 2 notions. So think of it as the mean preserving spread set of F. But let's be formal and start from here. So suppose that script L1 is the set of real valued bounded and integrable functions defined over 0, 1. I'm using the script because the regular L1 doesn't have the bounded property, but here I impose boundedness. So for 2 functions, such functions f and g, we say f majorizes g if these 2 conditions hold. The first one says that the integral of g should be at most the integral of f, where the integral is taken from t to 1, and the inequality should hold for all t. And the second one says that the inequality that we looked at earlier should be satisfied for t equal to 0 with equality. Okay. Oops. Yeah, that's good. Thank you. OK, so and we say f weakly majorizes g if the first condition holds, but the second condition may or may not hold. So let's define a set of constraints. These are the set of linear functionals of g. So integral of g, q, w, I, q greater than some constant. And each constraint looks like this. And we say g is C feasible if it satisfies every constraint in C. The main 2 definitions that we are looking for, the first one says define the mean preserving spread set of f as the set of all functions g that are increasing and f majorizes them. Okay. And the second one is just the same as the first one, except that we throw away functions g that are not C feasible. So we are taking intersection with this feasibility set. All right. So what we want to know is basically how do extreme points of the, by the way, I call these 2 objects the orbit of f and the constraint orbit of f for simplicity. And what we want to know is how the extreme points of the constraint orbit of f look like. And the motivation is Barr's maximum principle. It says that a convex upper semi-continuous functional u of f attains its maximum over the constraint orbit at an extreme point of it. So if we want to look at the optimal solution to this optimization problem, one way to understand how it looks like is just looking at the extreme points of this set that we maximize over. Okay? A remark here is that for the case without constraint, when the set of constraints is empty, this problem has been studied before by Kleiner, Moldovana, and Strack, and I'm going to talk about the connections between their results and our results a bit more later. OK, so here is our finding about extreme points of the constraint orbit. First 2 quick definitions. We say monotonicity binds at given a function g. We say monotonicity binds at a point s if there is an open interval to the right of s such that g is constant there. We say stochastic dominance binds at s if the integral of g equals the integral of f, integrals taken over from 0 to 1. Okay. Is there a question? OK. So and here's the theorem. Consider a right continuous extreme points g of the constraint orbit. There is a family of disjoint intervals such that outside these intervals, f equals g and stochastic dominance binds. Inside the intervals, monotonicity binds, and there are at most C jump discontinuities. It might be a little bit difficult to parse the theorem, so I will explain it on the picture. So the theorem says for any right continuous extreme point G, there are a family of disjoint intervals. Here I have shown them with these highlighted rectangles. Outside the intervals, the extreme point is just equal to the function f. And inside the intervals, the extreme point is piecewise constant. The number of jump discontinuities over all intervals is bounded by the number of constraints. Okay. And so I should mention that the results of Kleiner, Moldovan, and Strack implies this theorem for the case that C is an empty set for the case of no constraints, and for the general case that C is non-empty or proof builds on their work. In the interest of time, I wouldn't be able to go over the proof, but happy to talk about it with anyone interested after the talk. How much time do I have left?
1 minute.
Oh, OK. OK, so I told you about the results that I told you about how basically extreme points of the constraint orbit look like. I wouldn't be able to tell you how we apply these results to the monopoly pricing problem. I will just get to a conclusion. So we extend common frameworks in mechanism design by allowing the planner to impose additional linear constraints. Each additional constraint, as we saw in the structure of extreme points, appears as a one jump discontinuity in an iron interval. With few constraints, the structure of optimal mechanism changes a little bit. This is our observation from looking at the applications that we consider. And we also have a regularity condition in applications such as contract design and auction design guarantees non-existence of these jump discontinuities, and therefore the general structure of optimal mechanisms does not change under this regularity condition. All right. Yeah.
Thank the speaker. We're a little bit out of time, so suggest we go with continue with questions offline, and we continue with the next speaker.